Hello everyone, I'm Karthik and today I'll present the paper Synthetic Data Generation and Joint Learning for Robust Codemixed Translation. This work was done at LCS2 IIIT Delhi with my co-authors Sanjana Soni, Dr. Anup Kunchkutin, Dr. Tanmay Chakraborty and Dr. Shahad Akhtar. So what is code mixing or code switching as many people call it? Code mixing is a mixing of two or more languages in a single utterance. This kind of behavior is very common in multilingual communities like Hindi English, Spanish English, Cantonese Shanghais. So on the bottom, we see two examples. First one from a Hindi English code mix sentence, which we call English, and the second from Spanish English, also called Spanglish. So four out of the eight words in this Spanglish sentence are in English. So this is not pure Spanish. When we translate this code mix sentence into a non-code mix language like English, we call it code mix machine translation. So both sentences on the left are translated to the same English version. You are promoting them on all social media platforms. Now, starting with the challenges with neural machine translation models. The first one we all know that neural machine translation models like encoder decoder transformer models, but T5 all need vast amount of parallel data in order to achieve any satisfactory performance. By parallel data, we mean a sentence in language 1 as a translated version in language 2. For example, we see the English sentence "Hello World" is translated in French, and these two are parallel sentences. The second point is NMT models are brittle to even a slight amount of input noise. Slight variations in spellings and errors can lead to a totally different translated version, and we don't want that unexpected behavior. Interrelated to these are the challenges with code mix translation. First one is the unavailability of parallel code mix data. We find online social media as the only source of code mix text, and this text is raw and unstructured. Whereas in a normal non-code mix data, we find parallel sentences in like Hindi, Portuguese, and other high resource languages. The second challenge is there is no standardization available. The code mix sentences, when translated to English, are susceptible to spelling variation, typographical errors, and misspellings. For example, the word Q in Hindi can be written in three different ways by three different users: KYU, KYOON, KYUN, and all of them are correct. So there is no standardization available for code mixing. Next, coming to the contributions, our contributions are fourfold. The first one is we propose a pipeline for generating synthetic code mix parallel data from a non-code mix parallel corpora. Second, we released the first open source large scale in the English Codemixed parallel corpus, which has 4.2 million parallel sentences, along with a gold, dev, and test set. We call this dataset as Kinmix dataset, short for English Codemix data. Third, we also propose an architecture for robust Codemix translation. This is an encoder decoder model that can handle real world noisy Codemix input. And last, we show zero-shot performance from Bengali code mix to English code mix without developing a corpus for Bangla code mixing. Now, coming to the first part of this contribution, generating the data, parallel data for code mixing. The first step is deciding which language is the matrix language and which language is the embedded language. The matrix language is the main language which takes the structure of the sentence, and the embedded language is the language from which we choose the code mix words from. So in the right, we see Hindi sentence is the matrix language, and we replace the Hindi words with English, so English is the embedded language. The second step is to obtain the POS tags for each of the words and shortlist the words for the POS tags which belongs to the inclusion list. By inclusion list, we mean the POS tags for which the words will be replaced. So in Hindi, we commonly see POS tags such as nouns, identifiers, and adjectives being replaced by English words, and that's how code mix sentence is formed. And third is building a substitution dictionary so that we know for a Hindi word what's the corresponding English word we can replace it to form a code mix sentence. We form the alignment using fast align. We train an alignment model. We get the aligned words, and we now know which word needs to be replaced. In the green box, we can see the Hindi words and their corresponding aligned English words. So once we have the alignment, the next step is to choose words at random. which we can replace with the English words and form multiple code mix sentence. So on the yellow box, we can see the same Hindi sentence as multiple code mix English version depending on the words we have chosen at random. Once those words are chosen, we need to filter them using like probabilistic measures like perplexity or deterministic measures like how much percentage of code mixing is present in a sentence. If it's too high, then that sentence is eradicated, and we have shortlisted like a few sentences from a whole list of code mix sentence. The next step would be transliterating, or we also call it as romanization of Hindi code mix to a romanized version. So the orange box has the romanized Hindi Devanagari words in like English form. The last step is to add perturbation, the noise, which we call, so that it can mimic the real world code mixing behavior. We add four types of noise. We switch the letters, we omit some letters, we introduce some typos, we shuffle some letters from the word so that a noisy code mix version of the sentences are formed. Coming to the test set guidelines. So the gold standard test and dev set was annotated by two bilingual annotators, both aged between 25 to 35. Both had Hindi as the first language and English as the second language. So the guideline was they have to come up with a English version given a Hindi sentence in the first 5 seconds of the thought that comes up. Since there is no standardized romanization scheme, we told the annotators to use their own personal understanding of the word structure and the sound pattern to come up with different spelling variations. So this will account for the natural noise and help us understand the robustness in our trained models. So we see examples from our in-mix test set. On the left side, there is English sentences. The orange one are the highlighted English words. On the right, there are English sentence translations. So this is the parallel gold test data. Now coming to the dataset statistics. So the train set has 4.2 million pairs in 5 different forms: Hindi code mix romanized, and the noisy, and the English version. The development set has 280 sentences. Test set has 2500 parallel sentence pairs. We use two measures to understand the statistics. First one is the code mix index, which measures the percentage of code mixing in a sentence. And second is the switch point fraction, which calculates the complexity of the code mixing. It calculates the percentage of switching between languages in a single sentence. So if there is high percentage of switch, like one word is English, one is Hindi, then the SPF is large. But if there is like continuous English subsequence and continuous Hindi, then that is less switch point fraction. So dev and test set have higher complexity and higher code mix percentage. This will also help us test the robustness of our model. Also, test set have sentences which are much longer than what we train the model on. So token count of test set is 111, while the train set is 88. Now coming to the model that we train our data on. We call this model RCMT model, short for Robust Code Mix Translation. This is a single encoder decoder transform model trained in 3 different directions. First one is bidirectional Hindi English. On the left side, we see RCMT Roman. And we also add the noisy version to it, the Hindi code mix to the to the English translation. We only want the noise on the input side. Another version of this model includes the code mix version as well, the non-romanized one. So we call that RCMT Roman plus dev. So a proxy token is added on the decoding side so that we know what kind of language we want the translation in. 2EN means English, 2HICR means we want to translate the sentence to code mix Hindi. So the joint model is trained to optimize the cross entropy loss with label smoothing across all pairs. And this noisy data helps us to make the model more robust to spelling variations. Coming to the experiments and results. The first part is the model comparison. On the right, we see a table with 8 models compared with our proposed model. When we talk about the results, we see our model is all inclusive. That means it can handle code mix sentence, it can handle code mix plus romanized, it can handle the noise as well. It can even translate from English to a code mix version, which we don't discuss in this paper. So we see the improvement over transformer and convolution nets by a large margin. Training a single transformer model means we have to train n models for n different directions, but our model can do translation in all directions with a very high performance improvement we see. The next is we see the performance on multilingual models such as T5 and BART. So this MT5 and MBART don't have the Codemix version in their pre-training corpus. That's why we don't see a very good performance in code mixing as well, even after fine-tuning. And lastly, we do some comparison with the noise robust machine translation architectures. These models are very comparable to our proposed approach. We see MTT with a performance of 10.44 and our model with 11.54, which is very close. Next is the dataset comparison. On the table, we see four different datasets. The first one is the IIT Bombay non-code mix corpus. So we see our model works very well on the non-code mix datasets as well. Second is the spoken tutorial dataset, which includes the utterances transcribed from engineering and programming courses. We see a high performance on this because most of the POS tags in this particular corpus are proper nouns, which are easier to translate. Next, we come to the Lindsay corpus, which is a Twitter dataset, real world, very noisy, and our model has shown robustness to this particular dataset as well. So this is the closest dataset we can compare to in a real world setting. And lastly, we have superior scores on our own goal set. This shows that the model can handle longer sentences and much complex sentences that have higher switch point fraction and code mix index. Lastly, the zero shot results. So we trained the RCMT model that we showed before with the Bangla and English parallel corpus. For this, we don't have any Bangla code mix corpus. We call this ZCMT as zero shot code mix translation. Our hypothesis is that by including a code mix corpus of one language and a non-code mix corpus of another language from the same family, which is like Indo-Aryan for Hindi, Bengali, we can sometimes improve the performance without generating even code mix corpus for the new language. On the table, we see two models, the MMT and the ZCMT. MMT does not include the code mix version for the Hindi, but ZCMT does. And we see the performance improvement in ZCMT by a margin. Lastly, coming to the qualitative analysis and the limitations, the first one is the translation semantics. So on the right side of the table, you see a source sentence, a target sentence that's like the gold standard we want the translation to happen. And below that is the version that our model translated to. Even though the translation is good, this is not ideal to the translation that we want because the model has learned to copy the words from the source sentence to the target due to the way we created a data set, the alignment model. So the thought was translated to thought. Ideally, we would wanted like concept as a more suitable word. Second kind of error is the POS tagging error. For low resource language and for languages such as Hindi, since the pipeline has POS tagging as a step, our performance is dependent on this POS tagging. Uh, so if the performance of POS tagging is low, our substitution words will not be appropriate and the dataset will not be of very high quality. This will eventually creep up into the RCMT model that we trained on. And lastly are the alignment errors. So incorrect word mapping between the source and target can also completely change the meaning. So in the right side, we see an example, when are you coming back home, aligned with the Bengali version. Some words can have a single word mapped to many words. In this case, our model would fail, and that's how we see an error in the translation as well. Thank you for listening to the talk, and the codes and dataset can be found in this QR code. If you have any questions, you can contact us at these two emails.